Yeah, today I chose to show the background image once more of the VLTI, and one may see that the weather was not the best. Yeah, this may happen also, yeah, in Chile.
Oh, you
But
took the picture?
yeah, we took the
No.
picture. Yeah, it was exactly 2 years ago when we visited the
See.
site. Yeah,
Mhm.
yeah, and the small telescope that you see, uh, I don't know if yeah, this one small telescope. Yeah,
Yeah.
these are on the in the background. Yeah, and here are
Yeah.
three of the auxiliary telescopes. Yeah, so these are 1.8 meter telescope, and they are manufactured, yeah, in a company located about 700 meters from our home. Yeah, so very nearby.
Oh, awesome.
And
Great.
well, inside, yeah, you have the highest density of technology, yeah, regarding telescopes, because these telescopes, yeah, can be moved along the rails. Yeah, so there are railways, and they can be moved at any time, very easily, very efficiently. Yeah.
Okay, the big ones don't move, only the small ones move?
Yeah. So the big ones, yeah, I see. I think you. How many do you see? Two. Yeah.
Two, yeah.
These are the VLT 8 meter in diameters. Yeah. Rather than these are 1.8 meter in diameter. Yeah.
Is this the biggest movable telescope? 2 meters is quite big to move.
Well, these 1.8 meter telescopes, yeah, are probably the biggest which are movable, but the 8 meters, it's absolutely impossible, yeah,
Yeah, yeah.
to to move them, yeah, of course, yeah.
Combining all this light from all so many dissimilar telescopes must be challenging too, is it? Or
Well,
it's pretty
they never do it, yeah. They only combine either the four big telescopes, yeah, together, or the four small telescopes together.
okay, they don't
Yeah,
combine all.
no.
Is it technical difficulties that?
Well, yeah, there is a technical difficulty, yeah, which they could overcome, but at a quite a high cost, yeah. And the benefit, yeah, is not really great because well, you are sharing, different size up, well, aperture sizes, yeah, and it makes the data reduction and analysis, yeah, much more complex. So it's better to combine, yeah, similar aperture telescopes, yeah.
Cloudy skies are very rare there, right? What percentage of the year is cloudy?
Yes, well, the worst is in May, yeah, which corresponds, yeah, to winter, of course, yeah,
Right.
and depending on the phase of El Nino, yeah, which determine, yeah, the weather over the Pacific, yeah. Well, the conditions can be very bad, yeah, meaning that you may get snowfalls, yeah. Uh, but otherwise, apart from the months of well, April to June, the weather is usually very good. I think they get something like 275 photometric nights per year, yeah, which is a very
Quite high.
high number, yeah. Good afternoon to everybody, yeah, and good morning to some of you, yeah, who are not in India, but I think most of the participants, yeah, come from India, yeah. And today, what I would like to do, yeah, is still give you a very intuitive approach or view of what the Zernike-van Sittard theorem is, yeah. And for this purpose, yeah, I just made a video during the week, yeah, to make it even, much more intuitive, and then later on, yeah, I'll just summarize, yeah, the content of lecture number 7, which was on the video. And of course, there will be ample time, yeah, for questions, yeah. So first thing I will do now is just to share my screen. Yeah. So I have to pick up the open board. Yeah. Can you see the screen now?
Yes, we do see.
Yes.
Yeah.
So this is a video, and well, I just pre-recorded, yeah, the presentation, so that I will just let it go on. After, well, I stop the presentation. We can have a series of questions, yeah, on this. And well, if necessary, yeah, I will show once more the same video made out of GeoGebra applications, yeah. And then I could add comments, yeah, just to answer the eventual questions, yeah. So I just start the video now. So it is with the sound, yeah. So here is another animation illustrating the Dianic-Van-Sittert theorem. What is represented on the right is a small interferometer consisting of two pinholes separated by a baseline shown as red. Yeah. And then this corresponds, of course, to a spatial frequency, U, which is a baseline divided by the wavelengths. Yeah? And in this case, I've just considered that the wavelength lambda is equal to 1. As you may see, yeah, we may vary, yeah, the length of this baseline, and so also the value of that frequency. On the left side is represented a stellar disk, in this case with a radius of 0.5, which we may also vary, as you see, but I set it here to a value of 0.5 because it then corresponds to a diameter, angular diameter of 1 unit. Now the blue dots, yeah, is a one surface element, infinitely small, yeah, over the surface of the stellar disk, yeah. And we know that if the baseline, yeah, is not equal to 0 here, yeah, that the interferometer will show you, yeah, a series in the focal plane, a series of dark and bright fringes, yeah. And we may visualize this here. We see these fringes, yeah, alternatively bright and dark. Now, well, the goal of the Dianic-Van-Sittert theorem, yeah, is just to coadd, yeah, all the system of fringes due to all the surface elements, yeah, covering the circular disk of the star. Yeah. But what we know is that all the surface elements, yeah, which are located perpendicularly, yeah, to the baseline, which pass, yeah, through these blue dots, will give rise, yeah, to a similar series of fringes. Yeah? And so all this pattern of fringes, yeah, will reinforce each other and give rise, yeah, to, well, more conspicuous, yeah, a series of dark and bright fringes. Yeah. So I have illustrated, yeah, by means of the slice, the blue slice here, yeah, all those surface elements which would give rise, yeah, to similar pattern of fringes, yeah, just perfectly superimposed over the previous one. Of course, now, if we change the position of that slice slightly, as shown here, well, we see appearing in the focal plane a series of dark and bright fringes, but slightly offset, yeah, by an angular value which is exactly equal to the angle by which this slice is being shifted with respect to the previous one. So what we need to do is just to visualize, yeah, well, all the series of fringes, yeah, due to when we are slicing the stellar source. And of course, yeah, the strength of these fringes depends on the length of the slice, yeah. So the middle one, yeah, will give rise to a stronger pattern of fringes than the fringes rising from the edges of the stellar source. Okay, now we have here, yeah, a function, yeah, which just makes the coaddition, yeah, of those individual pattern of fringes and is represented here. So we see that, okay, the resulting pattern of fringes, yeah, will still be a series of fringes, but we see that the minimum doesn't go anymore to 0, yeah, which means that we are partially resolving, yeah, the stellar disk. Let's set now the baseline, yeah, to a much smaller value, yeah. So this is the frequency 0.1. We go very slow, yeah. And now, well, I show you here, well, the fringes due to this slice, yeah. So you see it's a slide. Well, it's a fringe, which is almost perfectly centered with 0, of course, yeah, and reaching a minimum here at x equal plus or minus 5. And just like before, let's move this slice, yeah, from the left to the right and see how all these fringes, yeah, superpose to each other. Well, we see here, because the value of the baseline is so small, so it means the frequency, yeah, spatial frequency, also very small, yeah, that they're almost all in phase, which means that when we will coadd them, yeah, they will reinforce each other and give rise, yeah, to this red fringe that you see, yeah, which visibility is almost equal to 1. Now we know that if we change, yeah, so I just stop this slicing. We know now that if we change the value of the frequency and go around 1.2, oh, that the contrast of the fringes, the visibility of the fringes, yeah, should almost be equal to 0. And here in this case, yeah, I reach a contrast or visibility equal to 0 for a value of u equal to 1.4. Also, normally, yeah, I should have reached that minimum visibility for a value of u equal 1.2. But the reason is that I didn't proceed with a perfect, well, integration, yeah, of all the patterns of fringes, yeah, but just with a finite number of them, yeah, equal to, in fact, 19. So a series of 19 fringes. So now I will show you here how the individual pattern of fringes look like. So I just move the slice, and here I see all the fringes, yeah, due to these different slices, yeah. So you see that by just making a coaddition of these, yeah, we find a resulting net system of fringes, yeah, which visibility is very near to 0. Now I just stop it, yeah, and now I will just move, yeah, the frequency a little bit above 1.4, 1.8, and we see here that, oh, the visibility, yeah, is very small, but not exactly equal to 0. Yeah? So it means that when we passed over that critical frequency, which is rigorously equal to 1.22, yeah, we see again, yeah, the small contrast in the fringes. Yeah. Now, if you would like to visualize, yeah, these individual fringes, yeah, I would proceed as before. Just move this slice, yeah, from the right to the left side, yeah, and we see these patterns of fringes individually. And now we have to coadd all of them, yeah, and well, it gives rise, yeah, now to a net system of fringes, which visibility is not perfectly equal to 0, but almost equal to 0. So, well, are there any questions regarding this video presentation about a more intuitive approach, yeah? Looking at the Zernike-Van Sittert theorem?
That was very good video, Jean. Things made it very clear.
Yeah.
Okay, any of you have any questions? You can unmute yourself and ask. So is this made with GeoGebra or?
Yes, it's made with GeoGebra. So I really recommend, yeah, to all of you, yeah, to download this very nice application, yeah, especially the 3D version, yeah, of GeoGebra, and it's so easy, yeah, to make nice simulations. It was developed by the Ministry of Education in France, yeah, and made freely available, yeah, especially for teachers in mathematics, yeah. But well, I find it so nice, yeah, to make illustrations, video, everything. So I really encourage all of you, you know, who likes mathematics, yeah, and physics, of course, yeah, to download this presentation.
Yeah, seems quite useful. So there's
Yeah.
a question whether in your simulation V equals 0. So U is B over lambda. I think it's talking about the second dimension.
Yes. So what is the question?
The question is, if U is B over lambda here, what
Yes.
is the second space frequency V?
Oh, yeah. Okay. So, well, in this case, yeah, V is equal to 0. Okay. So I just use the U. Yeah. Well, because the reason is the following. Yeah. You know that, well, the circular disk of the star, yeah, well, is symmetric. Yeah. So whatever is the orientation of your baseline, yeah, well, you will have exactly the same answer with your interferometer. Yeah, so you only need one parameter, which is a kind of radial, yeah, radial baseline. Yeah, and therefore, well, I just set the v equal to 0, and just let the baseline be represented, yeah, by u, which is equal to b over lambda. Yeah, is it okay?
We'll see if they have a follow-up. I think it was clear.
Yes.
Anyone else has any questions before we move on? I hope it was clear to everybody what was shown in the animation.
Yeah. Yeah. Okay. Now I will give you, yeah, some explanations, yeah, regarding this video. What exactly? Okay. So you remember during the previous lecture, yeah, we established, yeah, this equation to represent, yeah, the pattern of fringes, yeah, due to a slice, yeah, which intensity, yeah, at the position angle zeta was given by this expression, yeah. So you see here, it depends, yeah, of course, on the length of the slice, yeah. So we saw that for the circular disk of the star, the slice was the largest, yeah, in the middle, and when we were reaching the edge, yeah, it was getting smaller, yeah. So this takes the length, yeah, of the slice into account, yeah. Then times 1, because 2 times 1 is 2, is exactly, yeah, the intensity due to the 2 independent apertures, yeah. But then we have the interference term, yeah, which is represented, yeah, here by the cosine, yeah, of 2 pi times u, which is a spatial frequency. Then x, yeah, which is a coordinate, yeah, in the observer plane where you are looking at the fringe pattern, yeah. Well, this is the distance between the pinhole plane and the observer plane, and well, you just set it z equal to 1, and zeta, yeah, is the angular position of the slice. Yeah. Okay, now what we know, yeah, so we know how to calculate, yeah, this intensity for one slice, yeah, and of course for any point located on the slice, it would be exactly the same expression, but the intensity would be reduced, yeah, to the size of the, well, infinitely small surface elements that you would consider. Now, as written here, yeah, due to the incoherent nature of the light source, yeah, although systems of fringes, yeah, for different angular position zeta of the source, yeah, well, are independent from each other, and well, what will happen in the observer plane is that the respective intensities, yeah, will just be co-added, yeah, and therefore the resulting intensity distributions will be given by the integration of the previous expression, yeah. Now, what I did, yeah, on that video, instead of performing the integration, which I could have done, yeah, analytically speaking, yeah, well, I made use of GeoGebra, as you saw, and I performed, instead of an integration, yeah, a discrete summation of 19 terms as follows. So I just wrote that IT is equal to the summation from 1 to 19. Well, the intensity of one slice multiplied by the width of the slice, yeah? So more you put slices, yeah, well, better it is, yeah? Here I did it, yeah, for 19 slices, yeah? Now, if you take the expression from equation 1 and insert it here in this summation, this is what comes out, yeah? And now, well, you may distribute the summation sign, yeah, on the two terms here. and then you may divide, yeah, by well, the integrated intensity, which is just the summation, yeah, of the 19 slices, yeah, and you get this expression, yeah. And so this, what you see here, yeah, is absolutely, yeah, a Fourier transform, yeah, of the normalized, yeah, because divided by this quantity, intensity, yeah, of the source, yeah. So well, of course, yeah, for a Fourier transform, you would expect to see here a complex exponent, yeah, but this is a real part, yeah, of the exponent, yeah, and this is how it came, yeah. So, any question on this video presentation? Well, it will be made available to you. I'll send it here to Prakash, since there is some sound, so it makes sense, yeah. So if there is any question, yeah, or maybe later, then I'll skip and go to the next slide. So next slide, yeah, is about summary of relations derived during the previous lectures. So you will still zoom once more. Now I will center the screen. Yeah. So you remember that during the previous lectures, yeah, we established so the Zernike-van Sittard theorem, yeah, according to which the complex degree, yeah, of mutual coherence, yeah, is simply, yeah, the Fourier transform of the normalized intensity distribution of the source, yeah. And well, we introduce the two space frequencies, yeah, U and V, yeah, which are X over lambda and Y over lambda, yeah. And now, well, normalized intensity distribution means that, well, we have divided, yeah, this intensity by its integration, yeah, over the source extent, yeah. Okay, now in the video I showed you, yeah, I just considered that V is equal to 0, yeah, and made use just of the U spatial frequency for the reasons of symmetry, yeah. Okay. Now in lecture 7, so which means that the YouTube video that you have visualized, yeah, maybe during the weekend or before, well, we have demonstrated another theorem, which is, you know, very important, yeah, which is known as a fundamental theorem, according to which, yeah, the distribution of the complex amplitude of the electromagnetic field, yeah, in the focal plane is merely equal to the Fourier transform of the distribution of the complex amplitude in the pupil plane, yeah. So now, of course, the P and Q are variables, yeah, are also space frequencies, yeah, and they are defined as follows, yeah. It's x prime here divided by lambda f. Now the coordinate x prime and y prime, yeah, are Cartesian coordinates in the focal plane. Lambda is the wavelength at which we are making the observations, yeah. Well, always, yeah, in a quasi-monochromatic light, yeah. And f is the focal length, yeah, of your optical instrument, yeah. And so we see, yeah, the analogy existing, yeah, between these two, just a moment, between these two equations, yeah. We see that, well, there are just two Fourier transforms, except that here we have the UV space frequencies, and here we have the PQ space frequencies. And now, well, here, this is important, yeah, is that the intensity here has been normalized, rather than here, the amplitude, yeah, in the pupil plane, yeah, has not been normalized. Yeah? Well, we could normalize it, yeah, but it was not down in the lecture notes, yeah. Okay. Now, this means that, you know, all the results, yeah, we already derived, yeah, in the context of the Zernike-van Sittard theorem. Well, for instance, that, well, the Fourier transform, yeah, of a square star, yeah, is a product of two sinc function, yeah, or that the Fourier transform of a circular star, yeah, is a first order Bessel function, yeah, could be, well, all those results could be immediately applied, yeah, to the case where the aperture is a square aperture, or the aperture is a circular aperture, yeah. And it is exactly what we did in the lecture notes, yeah. So I will just shift, yeah, to the next slide here. Okay, I just zoom. To zoom, come here. Yeah. Now I just shift it down a little bit. Yeah. So you remember, yeah, for the case of a square star, yeah, we just wrote the expression, yeah, of the intensity distribution that has been normalized. And then when we compute it, yeah, the Fourier transform, yeah, of the normalized density distribution, we found that it was a product, yeah, of two sinc functions. Yeah? So now, exactly the same way, we could consider that, you know, the pupil is a square aperture represented by A, which means that you represent it, yeah, by the product of two-door function. Then we take the Fourier transform. Now you see, this is the fact that it has not been normalized. Yeah, you have the value of the amplitude, yeah, of the electromagnetic field in the pupil plane. We assume that it was A0, a constant. Yeah. Now we need, yeah, to normalize this function if you want to make helps of the analogy principle. Yeah. So what we do if you integrate, yes, this expression, so this one, yeah. So I will just use a laser. Yeah. If we integrate, yeah, this function over the square aperture, you'd find that it is equal to a square. So a being the side of the square. Yeah. So what we do first, we divide by a square, but if we divide it here, we have to multiply here. Yeah. So that we may write the sign equal. Yeah. And then we may immediately apply the results established before for the case of the Van Sittard-Zernike theorem, where we replace zeta 0 by A, the side of the square, and where we replace the frequency UV by PQ. Yeah. Okay. So we immediately obtain this result. And of course, yeah, if we represent the intensity in the focal plane, yeah, it is a square of the complex amplitude, but since it is real, it's just a square of this expression. So you see it here. And here we have the illustration, yeah? So here is a distribution of the complex amplitude of the electromagnetic field in the pupil plane. And here is a resulting image that you see in the focal plane, yeah? So it's something looking a little bit like the airy disk, yeah? But it's not an airy disk, yeah? It's a product of two sinc square functions, yeah? And here what we see is that the distance between the two first minima, yeah, is 2 over A, where A is the side of the square aperture, yeah? Okay, now, finally, I go to the more complex case of a circular aperture. So in this case, well, we just have to refer, yeah, to the Zernike-Van Sittard theorem, where we consider that the case of a circular star, yeah, uniformly illuminated, well emitting, yeah, in a uniform way, and which radius is rho UD, uniform disk, or the angular diameter theta UD, theta for angular diameter and UD for uniform disk. And we found that the expression of the complex degree of mutual coherence was twice, yeah, the first order Bessel function evaluated for this argument and divided by the same argument. Yeah. Now, well, B here, you see we don't have UV, yeah, because V is equal to 0, and U is equal, in fact, to B divided by lambda, where B is, of course, yeah, the distance between the two pinhole apertures, or here, well, yeah, exactly. Now, similarly, yeah, if you would like to know, yeah, well, what is the distribution of the complex amplitude, yeah, in the focal plane of a mirror which is circular in shape, yeah, or of a lens, optical lens, which is circular, yeah, well, we just apply the correspondence principle, yeah, so we say, okay, the distribution of the complex amplitude now depends only on one parameter, not on x and y, x prime or y prime, but just on rho prime, yeah, which is in fact, a radial distance to the center of the image in the focal plane. Now, this quantity, yeah, is just for reason of normalization, yeah. So it's a complex amplitude of the complex amplitude of the electromagnetic field, multiplied by pi r square, which is a surface, yeah, of the aperture. Now, factor 2, first order Bessel function, pi is okay. Now we replace, yeah, the angular diameter of the star, yeah, by the diameter of the mirror, and we replace, yeah, the space frequency u, this time by rho prime divided by lambda f. Yeah. Now, if you would like to know in the focal plane what is the distribution of the intensity, yeah, well, because the complex amplitude is real, so it's just the square of this quantity, and you end up, yeah, with this expression. Now, the illustration, yeah, is given here below, yeah. So we see that for the case of a circular aperture with a radius r or diameter d, yeah. Well, this is the Airy pattern, yeah. So you see how to get the analytical expression, yeah, of the Airy disk in the focal plane. Yeah? Okay, so this ends my presentation. So I just stop sharing my screen, and now I'm ready to answer eventual questions. Yeah.
Okay, so yeah, the setting is such that anybody can raise their hand on, just unmute themselves and ask a question.
Yeah.
Okay. I think Gitanjali wanted to ask a question, but I think she says in the chat that she understands it now. It was about one of the assignment questions.
Yeah, I think I understand it. I was getting confused about how to choose the correct aperture shape for given for a given object. Like that question was about actually to find your parameter by choosing the correct intensity model. So I think I get it because it was a square bulge. So the right aperture form would be choosing a box, a door function.
Yeah.
And
Correct.
yeah, so I think I now, after looking at the detailed solution, I understand it.
Yeah.
Yeah.
Mm-hmm. Absolutely. Yeah. Yeah.
Yeah.
Correct.
So if it's a bulge, so because the bulge was mentioned to be a box bulge, so we choose a door shape function there.
Correct. Yeah. Yeah. Mm-hmm. Absolutely. Well, one could also work, yeah, with well, elliptical shape aperture, which means that, you know, you would proceed with some apodization. Yeah, you agree that it would be very bright in the center, and then the reflectivity, yeah, would decrease as you go to the edges. Yeah, and if this function would be perfectly, well, elliptically shaped, yeah, what you would observe, yeah, in the focal plane, yeah, because it's a Fourier transform of an ellipse, yeah, of an ellipsoid, yeah, or of a Gaussian, yeah. I'm sorry, yeah. So I was thinking about the Gaussian shape, yeah. So
this question was regarding converting from intensities to visibilities.
From previous one, from intensity.
Yeah, in the previous assignment, not aperture shapes, but
yeah. No, I agree. Yeah, I agree. Yeah, but the point I wanted to make now, yeah, well, this is interesting. Yeah, everybody heard about apodization, yeah, of the aperture. What does it mean? Is that the reflectivity, for instance, of a mirror would not be the same in the center as at the edges. Yeah, so if you would use a Gaussian function, yeah, to represent this kind of apodization, the result would be that in the focal plane, you would obtain a Fourier transform of a Gaussian, which is still a Gaussian, yeah? And so the point spread function in the focal plane would look like, yeah, a Gaussian distribution of light. And this is interesting. You would not see anymore, yeah, the airy disk, yeah, but you would see a Gaussian, and you would understand that larger is the aperture, yeah, well, narrower would be the point spread function, yeah, still represented by a Gaussian, yeah. Because, well, of, all the properties of the Fourier transform, which were also, well described, by Professor Daesh, during the Wednesday lectures. So do you have more questions? So you see that Fourier transform, is a very, very nice tool, to play with, and well, there are many fields here where we may apply its properties. Now the next step, I think this will be the subject of the next lecture. Will be to apply the fundamental theorem to the case of two aperture, independent apertures, well distant by the distance b, where b is the baseline. So you see here, you will receive signal, here you will receive signal, but no signal in between. And so it will be possible to first treat the case of two square apertures, then the case of two circular apertures, and then we will know how an interferometer with finite size apertures is working, and what kind of one-spread function it delivers in the focal plane. So we are on the good way to reach our objective. And then, well, we will still have to discuss following items. First one is about UV coverage. One could wonder, well, depending on the latitude of your location and declination and right ascension of the star you are looking at, what is baseline orientation and the baseline length seen by the star, because this is the important quantity, is what is being seen by the star of your interferometer. And now a second well important item we didn't address yet, is about the phase information that we didn't consider yet. We only considered the module of the complex degree of mutual coherence, and well, we didn't mention anything about the phase information, and well, you will see that phase information, is also a treasure, but it's not easy to retrieve from the observations, so special techniques, will be needed, and we'll discuss those during the 3 remaining lectures. So, is there any other question regarding this lecture or the past lectures? It will be interesting for me to know, in case some of you download the GeoGebra applications and try to make use of it to simulate some situations, how difficult it was for you to handle this tool, and well, I may be ready to bring any help, because well, it's really very nice. Well, I really decided now for any illustrations accompanying the lectures or scientific papers, to make use of that tool, because it's so easy to make very nice figures, or video, It's a very ergonomic tool, very, very, very much.
Does it right now, so you have coded it such that it takes the Fourier transform of the intensity profile that you gave, right?
No. Well, you see, well, of course, there are always limitations somewhere, and so, well, it's not possible with GeoGebra, to implement the Bessel first order Bessel functions, neither the Fourier transform. So this doesn't work, and therefore, I try to, just to make something similar, by deciding to make a finite summation of a limited number of terms, and to see physically what it corresponds to. If I would have proceeded with an integration, probably I would have missed those aspects. And I think it's always very nice to be able to visualize what you're doing. Yeah. So probably for the Fourier transform and well, implementation of the Bessel functions, yeah, I would use other application software, you know, like well, I forgot now the names, but well, they are known by all of you, yeah. But I just forgot. Well, yeah. This was some sun from Belgium entering the VLTI in parallel. Yeah.
Yeah, we could see. So what you did in there was created separately the cosines as the fringes. So did
Yes.
you create that as a separate function and manually move it to the left and right and then take a video
Oh,
of it?
yeah. Well, not manually. This you could, you know, there is a special application which allows you uh, to do it automatically. Yeah. But unfortunately, yeah, the summation, yeah, of all those individual components, yeah, I had to do manually, yeah. So I had to write 19 times plus a cosine plus cosine plus cosine with a different value of zeta, yeah, yeah. And therefore, I didn't take more than 19 terms, yeah. But if you'd like to take 199 terms, you could do it, but it would take a lot of time, yeah. But well, yeah. So yeah, for yeah, usually you know when I would deal with the Fourier transform, yeah, I would use Python applications, yeah, directly, yeah. And but then you, of course, it's more like a black box, yeah. You're using already a fast Fourier transform, you know, codes which have been written, and you don't see anything, yeah. So it's nice to combine both, yeah, to make very rigorous applications, yeah. Just make your applications Python, and to visualize, yeah, this, yeah, just use GeoGebra, yeah.
Right. So in Python, you use discrete Fourier transform.
Yeah.
Right.
Yeah. There are many existing codes, yeah. So you don't have to rewrite anything by yourself, but just go on Google, yeah, and Fourier transform Python, and you find many already good codes which exist.
Mm-hmm.
Yeah. So the next lecture will be very interesting. You will see, yeah. So applications, yeah, of the fundamental theorem to the case of an interferometer, yeah, just to see what is a response function. And of course, the response function is always for a point-like source, yeah? Huh? For a point-like source, yeah? So how shall we go from a point-like source, yeah, to the case of an extended one, yeah? Well, there we will make use of the convolution theorem, yeah, which Professor Desch, yeah, spoke to us already about, because he said, well, when you make a convolution product, yeah, well, in the original space, yeah, it becomes, well, well, yeah, convolution product, yeah, becomes the simple product, yeah, of a two Fourier transform, yeah. So it's very easy. And I try to bring to your attention, yeah, a very natural case, yeah, of a convolution that we may see every day when going outside, yeah, and provided that there is some sunlight, yeah. I don't tell more now, so that participants, yeah, come to my next lecture, yeah. But it's a very nice demonstration of what a convolution product is, yeah. And with, of course, in the context of astrophysical applications, yeah. And well, inspiration, yeah, to find out, yeah, this natural product of convolution in nature came during a visit, yeah, at Iuka, yeah, because we saw, well, on the ground, on the walls, yeah, many illustrations of that convolution theorem. Yeah, if there are no more questions, yeah, maybe we will end now and reconvene. Well, on next Wednesday, yeah, Professor Desch, yeah, will give one more lecture, right, on Fourier transform. Am I right?
Yes, that's.
Yes, that's right.
Yeah, yeah. There is one hand raised. Yeah. Oh no, it disappeared. So do we agree? We stop here and say see you next Wednesday, and then hopefully next Monday. And you will see it becomes even more and more exciting. Well, now we had many, I would say, technical aspects of the Fourier transform, but one is to play with them and find that really it's a marvelous tool, and especially to understand, how it works, why it works, and so bye-bye to everyone. I wish all of you a very nice week, with sunshine if possible, and see you on Wednesday.
Okay, see you all.
Bye-bye, everybody.